The last topic I want to talk about in this video is conservation of momentum. We did this for linear momentum back when we defined momentum. We said that for Newton's second law of the derivative of the momentum with respect to time. And if we have an isolated system, we said there's no external force on the system, so the sum of the forces equals 0. That means that the derivative of the momentum is 0. That means that the momentum is constant. And that gave us conservation of momentum. Initial momentum equals final momentum. We can do the same thing when we're talking about angular momentum. We can write Newton's second law in its rotational form. The net torque is the derivative of the angular momentum with respect to time. An isolated system in this case means that the net external torque is 0, so no external torques. And that means that the angular momentum is constant and we have conservation of angular momentum. I have a special slide for conservation of angular momentum. So angular momentum is conserved when there is no net external torque on the system. The way that we use this equation, we can use it just like we did for the conservation of linear momentum. We can use it when we have collisions, as long as the net external torque is 0. And we would just sum up all the angular momenta of each object, the initial and the final. So if we have, for example, a rotating object that is colliding with an object that is moving linearly, we would just add up all of their angular momenta, initial and final, and solve for the unknown. And we'll do an example of this in the guided examples. We also have a special case when we're looking at a deformable rotating system. So what in the world does that mean? It's a case we see very often. Think of an ice skater. When she brings her arms in, she spins a lot faster. What is she doing when she's bringing her arms in? She's changing the distribution of her mass. The mass was far away from her body. She had a big moment of inertia. And then she brought him close. She reduced her moment of inertia. So whenever you have a deformable rotating system, which usually consists of it could be more objects, but the mass distribution is changing. Maybe some objects are moving closer to the center or further away from the center. Then we can use this form of the conservation of angular momentum. I omega initial equals I omega final. There's a very common demonstration for conservation of angular momentum. And I encourage you to take a look at this link. You can just YouTube MIT spinning bike wheel demo, and you'll see this video. It's where you hold this spinning bicycle wheel, and then as it's spinning, you're flipping it around, and then it causes your whole body to rotate. It's only a 2-minute video. If you have a chance to watch it, it's pretty cool. So we'll definitely do an example of a collision and also of a deformable rotating system. So lots of different examples in this video. The last thing I wanted to go over was just one more question. And it says, an ice skater spins with her arms stretched out to the sides. She then pulls her arms in so that her moment of inertia decreases by a factor of 2. What happens to her kinetic energy? So, we have to really pay attention to what the question is asking. It's asking about kinetic energy. When you're thinking of the ice skater, what hopefully comes to mind is the equation that we just talked about for conservation of angular momentum. I initial, omega initial equals I final, omega final. So if you're thinking, okay, her final moment of inertia is decreasing by 2, then that means that her final angular speed or angular velocity must increase by a factor of 2. So if you chose B as your final answer, you're almost there, but you really have to pay attention to what the question is asking. So if it asked for what happens to the angular velocity, then yes, it would increase by a factor of 2. Because if you have 1/2 I, then you must have 2 omega in order for the two sides to still be equal to each other. However, it asked what happens to the kinetic energy. we're talking about rotational kinetic energy here, since this is an object that is rotating. Rotational kinetic energy is 1/2 I omega squared. So this is a two-step process. The angular velocity or angular speed doubled, but now if we double the angular speed, what happens to the rotational kinetic energy? It's going to quadruple because we have the 2 omega is now squared. So we're going to have 4 times 1/2 I omega squared. We're going to have 4 times the rotational kinetic energy when the moment of inertia is decreased by 2 and we use conservation of angular momentum.